All right, let's just take a look at this side that says periodic table worksheet. Okay. Where do we find the most active metals? Bottom what? Bottom left. With francium being the most active metal. Where do we find the most active nonmetals? Top right. What's the most active nonmetal? Fluorine. Don't pick something from group 18. All right. I didn't tell you to skip number 3, but skip number 3 for a second. We'll come back to it. As you travel down a group, the atomic size does what? What do you think happens to the atomic size? Increases. Why do you think it increases as you go from top to bottom? More energy levels. Excellent. More energy levels. So if you look at, let's say we take the first, ooh, we're blurry. Come on. We take group 1, and let's just look at group 1. We'll take sodium, potassium, and that's my periodic table. Okay. Sodium, potassium, and rubidium. Let's just take those 3. Okay. Sodium, here's its nucleus. It has 1, 2, 3 rings, 3 energy levels. Potassium has 1, 2, 3, 4 energy levels. Rubidium has 5 energy levels. 4, 5. When we are looking at the size of an atom, we are looking at it from the nucleus to the outermost energy level. So this is called the atomic radius. As you go down a group, the radius increases. Okay? We will get back to what happens across a period in a few minutes. All right. A negative ion. Is it larger or smaller than its parent? Dylan, what do you think?
Larger.
Why? Wrong. It is larger, but it's not larger because it gains an electron. It's larger because when you shove that electron into that energy level, that very outside energy level. So let's say we take fluorine. Fluorine looks like this, where it has 9 protons. Then it has 2, and then it has 7. I was messing with my colors before. Okay. If I put another electron in here, okay, I am not getting bigger because I'm putting an electron. Electron is so small that it's not going to affect the size. However, what you are doing is you are shoving another electron onto that outside ring. And every electron is negatively charged. And what do negatively charged particles do to each other? They repel each other. So if I shove another negative on here, now all of these negatives just push a little bit further apart from one another. And so therefore, this ring gets a teeny tiny little bit bigger. That's because the electron gets shoved in there. It's not because you're adding an electron. It's because there's more electron repulsion in that ring. Okay? You see the difference? Okay. What happens when you get a positive ion? If a negative ion gets bigger, what is a positive ion going to do? Get smaller. Why does a positive ion get smaller? Think about what's happening with the electrons. Hold on a second, Dylan. Go ahead, Ange. What? But what? Yep. But if I said you can't get bigger because you're gaining an electron, you can't get smaller if you're losing an electron. What are you actually losing when you lose that electron? Huh? Kind of. Let's look at a sodium. Okay, so here's the sodium nucleus. The first ring, second ring, third ring. The first ring you have 2. The second ring you have 8. Third ring you have 1. That's a sodium atom. You see it now? Okay? When you become a sodium ion, what are you losing? No, you're not losing the atom. You lose the electron. But when that electron goes away, what else is going away? The ring. So instead of having 3 rings, you now only have 2 rings. And so if I'm measuring the size of the atom, I'm measuring from the nucleus to the outside. This is going to be bigger than if you only have 2. So when you become a positive ion, a cation, you are going to become smaller because you are losing a ring, which is also called an energy level. Okay? When you are negative, you are becoming bigger because you are putting another electron into the energy level, and the energy level, the electrons are going to repel each other just a little bit more, and they're going to get a little bit bigger. Okay, so I didn't really go over that yet, but now we did, so now you understand it. Okay, 7, 8, 9, 10, we was going to do that today. What are elements of group 1 called? Dylan? Alkali metals. What are group 2 called? Diego, what's group 2 called? Perfect. Alkali earth metals. Groups 3 through 12 are called, Mia? Transition. What makes them so special? What makes a transition metal so awesome? Uh-oh. Nobody remembers? I know I talked about this. They make pretty colors. Remember that? They make pretty colors when they are in solution. So write that down. They're pretty colors in solutions. A solution means when they are mixed with water and they are actually forming ions. Okay. As you go from left to right across the periodic table, the elements go from metals or nonmetals to metals or nonmetals. So as you go from left to right. What do you think, Kyle?
Metals to nonmetals.
I love it. Metals to nonmetals. Group 17 are called halogens, also known as the salt formers. The most active element in group 17, fluorine. He's the bully. Okay, group 18 are called the, James? Noble gases. 18 I crossed off. Elements within a group have a similar number of, so if they're in the same group, what do they have the same number of? Valence electrons. And what does that do for them? Makes them have similar chemical properties. You guys awake this morning? Similar chemical properties. All right, elements across a period. They called it a series, but periods is what the Regents calls it. So as you go across a period, what do they have the same number of? Christina, what do you think? Do you think anything? She doesn't think anything. Okay, we need to send out an SOS. Ange, go. They have this similar number of energy levels. Okay? So, Christina, that means they have the same number of rings. As you go across a period, and if we pull up a periodic table here, let's pull one up just so we can see. Reference tables. Let's go down. Okay? All the elements that are in period 2 have 2 rings. First ring has 2, second ring has either 1 or 2 or 3 or 4. So they have 2 numbers here which represent the number of rings or energy levels that they have. Everything in period 3 has 3 rings. Period 4 has 4 rings. Period 5 has 5 rings, and so on and so forth. Okay, a colored ion generally indicates, if you have a colored ion, what do you have? Transition metal. I lost my place. Transition metal. Okay, as you go down a group, the elements generally become more or less metallic. As you go down. More. Okay? So, again, I told you it's hard to see it over here, but over here it's pretty easy to see because carbon is a nonmetal, silicon is a metalloid, germanium is a metalloid, and then tin and lead are true metals. So as you go down a group, you get more and more metallic character. That's the words they're going to use. All right, the majority of elements on the periodic table are metals. Elements in the periodic table are arranged according to their... Hold on a second, Ange. Allison, are you awake back there? How do we arrange the elements on the periodic table? According to their... I can't hear you. Atomic number. Good. And if they have both metallic and non-metallic properties, it's called, Caleb? Metalloid. Awesome. Flip it over. All right, let's go. Which one is an alkali metal? I like C. C is a good answer. Okay, why is it not I? It's not connected, and it's also hydrogen, which is not a metal. Good. All right, an alkali earth metal is going to be F. An inactive gas, A. An active non-metal, H. I like H better. A semi-metal, B. Okay, B looks good to me. All right, and transition element. Okay, E or D. Because they said inner transition, the answer is really D. Okay, what that means when they say inner transition, remember this lanthanide and actinide series? They are inside here. They're right here, and you have to put them inside. That's why they're called inner transition metals. Most common oxidation state is -2. Which one? G. Good. A metal with more than one oxidation state. Now we're going to hit E. Okay. So these transition metals generally have more than one transition state. A metal with an oxidation number of +3. Where are we going to find elements with a +3 charge? Say it again, like you mean it. Nope. C would be +1, right? So if we look at our periodic table, all of these are going to be +1. All of these are going to be +2. Then we have our transition metals. What are all these going to be? Group 13 going to make +3s, right? So let's go back here and let's find group 13. And one that's going to be a +3 is going to be J. And then finally has oxidation numbers of +1 and -1. Which element has +1 and -1? I. All right. How do you feel about this stuff so far? Let me turn off this. Periodic trends that we're going to be talking about. Periodic trends. We've kind of already talked about this one, reactivity. You know where the most active metal is. You know where the most active non-metal is. Okay, so we've kind of talked about reactivity. What is a trend? Okay, when something usually does something. What's a trend that you guys are like in the middle of in your teenage years here? Hoodies. Hoodies are a trend. I know it's weird, but you know, we didn't always have hoodies. What else could be a trend? What do you guys do? Say it again. Stanley Cups is a trend. Now it's starting to move to a different kind of cup, whatever the other cup is, the Wallow cup, whatever. But water bottles are a trend just in general. Okay? I'm trying to think of some other things that you guys are familiar with that are trending right now. You know, like on social media, they'll say, "Oh, this is trending." What does that mean? It's popular. It's starting to go in that direction. That's what a trend is. So when it becomes popular, like let's make our own trend. Our own trend could be like wearing clown noses, right? If I start wearing a clown nose, that would be a cool trend, right? I could wear a clown nose, and then maybe Kyle comes in next day, he's got a clown nose on, and then Adrian's like, "Oh, that's the coolest thing I ever saw," and he starts wearing a clown nose, and next thing you know, like 50 people are wearing clown noses, and then the whole school is wearing clown noses. That's a trend, okay? It's going in that direction. Eventually, trends stop, and then something else takes their place, okay? A periodic trend means that something that is happening is going in that direction. So when we look at, let's say, reactivity, which we kind of looked at already, as you go from top to bottom in this group, what happens to the reactivity? It increases. Its trend is that it is increasing as I go down the group. Okay? Now, we're going to look at a couple of different trends. The first one that we're going to look at is atomic radius. Atomic radius. Now, atomic radius is measured. I had to cross this off because I guess when I made the PowerPoint, I forgot to take off what the placeholders were. Atomic radius is measured from the nucleus to the outside energy level. Okay. So, if I have a element like lithium, and I am going from lithium to sodium, what happened to the radius of that atom, or those atoms? It increased. We kind of did that when we were going over the worksheet, right? So the trend of atomic radius to go from the top to the bottom of this group is to increase. That's the trend. What happens as I go from left to right across a period? What happens to the radius? Be very careful. I want you to think before you say anything. Did we get any change in the number of energy levels as we went across? No. Okay. So if we're looking at period 2, from lithium all the way to fluorine, here's lithium and here's the fluorine. I want to know what's happening. What's the trend from lithium to fluorine? Is the radius going to get A, bigger, B, smaller, or C, not change? Oh, I got some of the same hands. Go ahead, Adrian. You would think it stays the same. Okay, that's what you would think. That is not what's happening, but that's a really good answer. Okay, because you would think, because I didn't change the number of rings, I am not going to change the radius of my atom. However, what did change as I went from left to right? The number of valence electrons. Very good. What else? The amount of space between them. I don't know what that means, really. What does that mean? Did they get further apart? Well, you put more. Yeah, okay. They kind of got a little bit further apart. I'm going for something else here that we're not hitting on. What's in the nucleus? Protons are in the nucleus, right? Aren't protons in the nucleus? And those protons are positively charged. Okay? So let's just look at, I'm going to do lithium all the way. Lithium. I'm just writing this down so you can see it. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. I'll stop there. Okay. Here's my nucleus, and I've got 2 rings on this guy. This has 1 valence electron. And then we've got beryllium. It's got 2 rings, and he's got 2 valence electrons. This guy has 3 protons. This guy has 4 protons. The electrons are negatively charged. The protons are positively charged. Okay, I didn't do the kernel electrons. I just did the outside electrons. These positives are pulling on these negative electrons. When we get all the way to fluorine, fluorine has 9 positives with only 2 rings. Don't worry about the colors here. Okay, I just didn't switch them. What's going to happen when these 9 positives are pulling on these 2 rings? Think. Let's say I have if these are people, okay? 3 people playing tug of war against 2 rings, 2 people. 3 people against 2 people. 4 people against 2 people. 9 people against 2 people. What's going to happen? It's going to shrink. And it's shrinking because the number of positives that are in this nucleus are getting stronger, and they're pulling on the same number of rings of electrons. Not the actual number of electrons, but rings of electrons. Okay? Now, here's the thing. You don't need to memorize this, but you do need to know it. So I want you to flip your reference table to table S. It's the next page. In the very last column, at least I hope it's in the very last column. I'm going with the very last column. Okay? It says atomic radius. Do you see that? Okay. Let's look at the radius of lithium. 130. So I'm just writing that here. 130. Then we're going to look at the radius of fluorine, which is all the way over here. And that radius is only 60. What happened to the radius as I went from 130 to 60? It decreased. Why did it decrease? The protons had a stronger pull on those energy levels. Okay? So that's why it decreased. Now, if we looked up, somebody have their reference table in front of them? Look up beryllium, please, and tell me what the number is for radius of beryllium. What is it, 99?
Yeah.
Boron is 84. Carbon, 75. Nitrogen, 71. Oxygen, 64. And 60. Okay, this one, of course, doesn't show that. But you see how it goes down as you go across? Every once in a while, it'll do this. Okay, it'll go up, it'll bounce down. This one happened to all just go down. But every once in a while, it'll bounce up and down in here. When they ask you what the trend is, this is probably the most important thing I'm going to say all day. Sean, you ready? Okay. You look at the first one, you look at the last one, and then you'll know what the trend is. Do not look at what's happening in between. Okay? Because there might be, this guy gets a Stanley Cup, this guy gets a Stanley Cup, this guy gets a Stanley Cup, this guy gets a no-name brand, this guy gets a Stanley Cup. So there might be a couple outliers. Always, when you're looking at trends, you want to look at the first one, you want to look at the last one. All right, let's do trend going from top to bottom. So from lithium all the way down to francium. So I'm going to go from here, lithium, to here, francium. So sodium, potassium, rubidium, cesium, and francium. Okay, I want the trend from lithium to francium. We already know what it's going to be. We know it's going to get bigger. But I want you to find it on your table S so that when you're doing the question, you know where to look. Lithium, we already said, was 130. What's francium? 242. Do we care what it's doing in here? Nope, don't care. Could be bouncing around a little bit in there, but the general trend is to go from 130 to 242. It is increasing. Okay? That's atomic radius, and it's given to you on table S. All right, the next trend that we're going to look at is something called ionization energy. Ionization energy, you got to write this down because you need to know what ionization energy is. Ionization energy is the amount of energy required to remove an electron. Write that down. I know we're going to end up running out of time. When ionization energy is low, it is easier to remove an electron. When ionization energy is high, it is harder to remove an electron. So ionization energy is basically the amount of energy, the amount of money that you have to walk up to somebody with in order to get the electron away from them. If energy is money. Okay? It's easy to remove electrons from metals. It's hard to remove electrons from nonmetals. Think about that for a second. It's easy to remove a metal electron because it's on the left side of the periodic table. They want to lose their electrons. It's harder to remove a nonmetal's electron. So what do you think the trend is going to be across a period from left to right? Ava, you look confused. You all right? What do you think the trend is going to be as I go from left to right? I can't hear you loud. I can. Metals are easy to remove their electron. Nonmetals, which are on the right side, hard to remove their electron. So what's going to be the trend of the ionization energy from left to right? Is it going to increase or decrease? It's going to increase. It's going to get harder to get an electron away from the nonmetals. We will continue with that tomorrow after your quiz. Yeah.